Hello everyone. Thank you for joining me today. So myself, I'm Pravi. So we are from the group 40. So I'll be presenting our midterm project on the content-based image retrieval or CBIR for the short. So this project was completed as a part of our image analysis course, and we are the group 14 in this presentation. So I will walk through why CBIR matters, what others have done in this field, so how we designed and implemented our frame, so what results we achieved, and where the system can be improved in the future. So why the visual search? So why the visual search matters? So as the world becomes increasingly visual, so billions of the images are uploaded daily on the platforms like Instagram, Pinterest, medical databases, for example. So the traditional keyword based search does not always captures the true visual content of the image. So keywords can miss the colors, the textures, or the spatial relationships, for example. So if I type a red car, I might miss the car that are maroon or the crimson or even mislabeled images. So that's where the CBIR comes in. So by analyzing the actual vision content, colors, shapes, textures, CBIR allows for more precise, intuitive searches. So this is important for the domains like the medical imaging, where the doctors might search for the similar cases, the e-commerce, where customers want the visually similar products, and the security, where analysts might track the peoples or the object across the footage. So, uh, so now let's define the CBIR fundamentals. So, content-based image retrieval means automatically analyzing an image visual features such as color distributions, surface textures, or the geometric shapes, so that computers can find the similar images. So, unlike the manual tagging, so which is subjective and error prone, the CBIR enables that the computer to see the image by looking directly at the pixels and the patterns. So this bridges the gap between the human visual perception and the computation analysis, so making it a cornerstone of the modern image search systems. So the literature review. The historically, the CBIR research focused on the handcrafted features like the color histograms, were one of the earliest and the most widely used methods. So they are the fast and effective, but ignore of the spatial layouts. So the two images with very different structures but same color distribution might look identical to the system. The texture features such as local binary patterns or the gray level co-occurrence matrices capture the roughness. So these can be highly the discriminative for the materials like the fabrics, but they are computationally more expensive. The shape features rely on the edge detections, but and the descriptors like the hue moments, they are strong for the object recognition, but requires the accurate segmentation, which is not trivial. So each of these has the strengths, but also the weaknesses in the scalability, the robustness, or the generalization. So in the recent years, the deep learning has revolutionized CBIR. The convolutional neural networks, or the CNNs, can learn the hierarchical visual representations directly from the data. So the pre-trained models like RESNet, VGG produce the embeddings that capture the semantic meaning far better than the handcrafted features. So the challenge, however, is that CNN demands the larger datasets and the higher computational power, so which makes them less practical in the lightweight or the real-time systems. So while the deep learning offers state-of-the-art accuracy of the traditional methods like histogram remains the valuable uh, when efficiency and the simplicity are required. So the framework and the pipeline. So our framework follows a systematic pipeline where you can see the process begin with an input image where we call it as a raw image. The pre-processing sorry, such as resizing, the color coding, and the normalization. Then we perform the pre-processing step, such as like the feature extraction, like creating a compact numerical representation. So these feature vectors are stored in a database. So when a new query comes in, so we extract the features in the same way and compare it against to the uh, stored data using the similarity matrix. Finally, we return the ranked results in a sorted form from mostly similar to the least similar. So this design ensures that efficiently scalability and accuracy. So we utilize the comprehensive data set which we got it as a part of the assignment where it contains of the hundreds of the images for the testing and the evaluation of the process. So the uniform so we specifically used a subset of the controlled testing where the ground truth reveals the labels are available. So all the images were standardized through the pre-processing steps. So as we discussed in the earlier the flow chart, the flow like the uniform resizing to ensure the fair comparisons, the 6-bit color coding to reduce the computational complexity while retaining the essential visual details. So the normalizations to make the feature extraction consistent regardless of the image size. So this standardized the dataset from the backbone for the reliable testing. So instead of comparing so the millions of the pixels, so where we standardize it to the 256, so that we'll be getting the limited set of the pixel values comparison with all of the others. So the image processing, the feature extraction strategy. So our chosen primary feature was a 6-bit color histogram. So resulting in a 64-bit representation for each image. So this balances the speed with the discriminative power by quantizing the colors where we reduce the redundancy and focus on the essentials color distributions. So we also experimented with extractions and the CNN features, while the CNN offered the stronger semantic understandings. So thus the histogram approaches was optimal for the real-time CBIR prototype. To enable the retrieval, so we built a feature database. So step one, for every image, we generated a 64-bit dimensional feature vector to store those vectors in the matlab.mat file for the efficiency. So applying the normalization to ensure the fair comparisons, especially between the images of the different sizes. So this database structure ensures that the similarity calculations are fast and reliable. The query processing and the similarity matching. So uh, when a query is submitted, the system extracts its features and then compares them with every vector in the database. So we used two similarity measures, the Euclidean distance and the cosine similarity. So the Euclidean distance, so which measures the absolute differences between the pixels. So whichever it is nearest to those pixels, so it will consider it as a similarity of the image. So the cosine similarity, so which measures the angular differences between and the scale of the variation. So this system then ranks all the database images by ascending distance, returning the top matches throughout the experiment. So we found the cosine similarity provided. So 7 to 9% of the better accuracy compared to the Euclidean, so which is the important insight. So the results. So here are the some successful retrieval examples for the nature scene. Uh, so the results are demonstrated that even a relatively simple histogram approach can be highly efficient uh, across the varied image categories. So for every coin, there will be like the two faces. So despite of the strong results, our system has a some of the limitations which are very clear. So the first, the handcrafted features like the semantic depth. So they cannot tell a part of the two different objects with the similar colors. Second, there is a data set bias. So the limited training diversity and affects generalization under the lightening the viewpoints. So these challenges are highlight why the future work should be included in the deep learning and the hybrid methods. So our analysis showed that the cosine similarity consistency outperformed the Euclidean distance across all the categories. So the improved was the dataset about 7 to 9% of the consistent. So this means that lightweight CBAR systems, the cosine similarity should be preferred metric. So especially when the feature normalization is applied. So there will be a demo like how we calculated all these results. I will be showing in a moment. So now I'll demonstrate how our CBIR ranks the images between them. So in step 5 we computed the Euclidean distance between the query image and the each image. So in the database, the smaller the smaller distance means the higher the similarity. Here the ranked matrix where the column 1 is the image index and the column 2 is the distance of that one. The first two rows of the close. So for this one, we used the MATLAB's the sorting the rows to sort the distances in the ascending order to give us the rank of the each image. So this ensures that mostly visually similar images appears first in the ranking. For consistency, we used call image 101.jpg. So as our query image, so that the top ranked results can be verified against the previous steps. So for this one, you can see that the rank distances dot mat where it was stored in the meta file. So in the step 6, okay. So in the step 6, we extended our CBIR framework to visualize the results. So first, the query image is displayed at the top of the figure window. So below is the query image, like where we displayed. Okay, you can see over here. So below is the query image, so where we displayed the top 20 retrieved images in the ranked order. So the first image here is the closest match. The first image is the closest match, and the rest follows according to the similarity of the score. So the good retrievals so the matches that are visually very similar. The false positives are you can see at the down below, which are like the most of the retrieved images are closely to the resembled of the query. So this demonstrates that effectiveness of the combined the feature approaches. So each the subplot title shows that the original file name, making it easy to trace the image back to the dataset. So we have the code snippet for this one where we can everything